Good afternoon, ladies and gentlemen. Welcome to this CEDA webinar on assessing and evaluating environmental turbidity limits for dredging. My name is Frederik Rose. I'm the chair of the CEDA Environment Commission, and I'll be moderating this webinar today. Well, CEDA is an independent and international membership-based professional network that brings together individuals and organizations from dredging, construction, and marine and maintenance of water-based infrastructure. And the CEDA Environment Commission is implementing CEDA's environmental policy and contributing to publications on environmental topics. So the topic of today is about the assessing and evaluating environmental turbidity limits for dredging. This webinar is also resulting from a CEDA information paper, which was published in May this year. This paper has been produced as there were indications that there is a need for guidelines on how to set realistic and effective environmental turbidity limits for dredging. So the objective of this webinar is to present the results and the findings of this paper and also allow some questions and discussions afterwards. The paper will be presented by Klaus Bunkart from NIRAS in Denmark. He's a senior consultant at NIRAS, and by Alessandra Feola, researcher at ISPRA in Italy. This webinar is also supported by Deltares, and we also have Edward Melger to support us on the technical issues of this webinar. We will have a presentation of about 40 to 45 minutes and some time for questions and answers afterwards. During the webinar, you can use the questions function of GoToWebinar if you have questions or need technical support. So enjoy the webinar, and I will now give the word to Klaus Bunkart to start the presentation on the webinar. Enjoy.
Hello, everyone. I'm Klaus Bunkart from NIRAS in Denmark. I am the chair of this working group for setting guidelines for assessing and evaluating environmental turbidity limits for dredging. Long word, a long list of words. This came out of, as Frederick says, out of the CEDA Environmental Committee. Well, really, it came out of a few people having a discussion. It was me, Mark Bolland from IMDC, and Astrid Kramer from Boskalis, who had a discussion on whether or not turbidity limits had the function they were supposed to have. And this kind of came on to say, okay, let's ask the dredging industry what they think. And then we made a questionnaire, which was passed around at CEDA Dredging Days some years ago. And the response was actually quite interesting because it showed, I was expecting it would show that the commercial dredger would think that this was something that was slowing down the work and stuff like that. But it wasn't. It was there was a consent that this was a good thing. It was if it was said correctly, it would benefit everybody. But if it was said wrong, it could harm either the dredger or the environment, depending on which way it was said wrong. It also showed that there was widely the term turbidity was misunderstood as a unique proxy for environment, which it is not. And there was, in general, an understanding that this was something that we would have to discuss. So I came back to the Environmental Committee, who issued this or started this process against this information paper, which all this work comes out of. And the working group was quite popular, actually. There was a lot of people who wanted to get into it. quite fast, and this is just the list of people in it. There is a long list of people who were supporting it from behind these people, but as you can see, it's a lot of interests around Europe in this area. Everything from Fehmarn to the port of Antwerp to Ispra, which is and Jan de Nul or Van Noord, or everyone who works with this has expressed an interest to some level to be part of this. So that was quite a good thing. So we had the first discussion, which was who has an interest in these turbidity limits. And well, there are a lot of people who has an interest, but it's generally the environment, of course, whose main interest is do not harm the environment. There is the authorities who want something that you can administer up against, and whereas you somehow can keep the public's interest safe. And then you have the project, which of course has an interest in getting the project going and keeping the costs down. So it's three different entrances, which of course has a common in the middle. But in general, those are the ways that this is looked at. So how do you do this if you want to set a turbidity limit and you kind of want it to fit in between all these things? Well, we had a discussion about that, and where I come from, you take a physical approach to that or a biological approach to that. Some of the others had a more practical approach to that, and it was actually a quite interesting discussion. But at the end of the day, it comes down to an integrated approach, which takes more or less all aspects into account, and where you look at all the points that actually feed into this. And basically, it is, of course, which environment are we working in? What's the hydrodynamics? What kind of sediment and which biology are we talking about? What do we intend to do? Are we dredging a small hole or a big hole, or is it a moving operation or a operation that stays in the same position? Which sensitive receptors do we have? Is it corals? Is it seagrass? Are there any kind of sensitive receptors at all, or what are we talking about? What is it actually possible to monitor in this area? There are areas where the background turbidity is so high that it's almost impossible to monitor a turbidity plume, but there are also areas where it's crystal clear and you can monitor almost anything. And then again, at the end, once you've done all these things, what response options do you have? What can you actually do to limit the impact? So that was kind of the outcome of the first discussions we had. Say, okay, this is the way we want to go. This is the kind of approach we want to discuss, and this is what we're going to do. And then that, of course, it is engineers. A lot of them comes down to some kind of a flow diagram where you have, of course, the yellow parts, which is the local environment. That was the first thing I mentioned. And then you have the baseline monitoring, which is the green at the top. And the orange parts are, once you know those things, then you can plan what kind of dredging you want to do. And then in parallel, you develop what the stress factors and how you can manage the environment. And then you come down to an iterative process where you at the end up with some levels during which you can start responding, and you can respond, and at the end you can do some mitigation. I'll come back to that, or I will not, my colleague Alessandro will, but this is the basis of our line of thinking. Before we do any of all that, we have to discuss a little bit of what we mean by turbidity, because this is one of the things we ran into, is that turbidity is just, widely used as a measure of the unclarity or the clarity of water, but it can mean a lot of different things. In this paper, we will of course discuss the different terms that could be turbidity, but we will use turbidity as a general term covering a lot of different measurement types turbidity could be NTU and FTU, which is actually light scattering. It could be SSC, which is SSC, TSS, or PPT, which is concentrations, or it could be something else. But at the end of the day, it is the amount of sediment in the water we are discussing. And then we'll come back to why it's a big problem, whether it's SSC, FTU, or NTU we're talking about. That part we'll come back to later. But for now, turbidity is a general term covering all of these things. The first thing we were suggesting to do is to find out which system are we operating in. And as I said in the beginning, it's very important to know whether we are in a shallow area with no waves and no nothing, or we are out in the ocean where big waves are operating and you can expect a lot of sediment in the water. So you have to go into and look to the beginning. What is the mid-ocean conditions? What kind of environment are we actually in? Are we in a lagoon? Are we in the open sea? Are we theoretically in a lake? Where are we? And once you know that, and it's logic for the next part to go and look at what is the sediment dynamics really? What is the background concentration? How do things behave? What kind of sediments are we actually talking about? And that goes for both the background sediment, but also for the sediment you intend to dredge. That is probably not the same. And then there's, of course, the biological aspects. Who lives here? Is it seaweed? Is it fish? Do we have some sort of very endangered species? What do we have in this system? And at the end, the one that often gets a lot of attention, the anthropogenic conditions, which is human activity. And if we take them from the mid-ocean, is of course wind, wave, current, salinity, and temperature, the most important ones. Wind, because it governs where the plume goes, at least at the surface. Waves, because it keeps sediment in suspension. Currents, because it's the main advection dispersion factor. It's where the main part of the water goes, and thus also the sediment. Salinity and temperature primarily influences settling velocities and in the verticals, so that's not that important, but still quite important. So once you know this, then you know a lot about what the background conditions are going to be and how the variations of the system, or the normal variation of the systems, are, both in terms of bed levels, in terms of background conditions, and also indirectly in terms of what the biology is. And there's the sediment dynamics, of course. What kind of sediment do we have? And like I said, it's the sediment at the surface first, but then secondarily also the kind of sediment you expect to release when you start dredging it. Secondly, it's the behavior of background concentrations. And why is that important? It's important because you are comparing an excess concentration which you get from the dredging operation to the normal variations of the background concentration. So without knowledge of that, you cannot kind of say anything about what the impact of an excess concentration is. And then, of course, the behavior of deposition and erosion. Also, that has to be taken into the equation. So then, once you know all that, then you're quite close to knowing quite a lot about what the biology is, because different species require different sediment conditions. But at the end of the day, you need to know who lives in this system. The crustaceans and the algae and the plants are usually the food for the fish, the birds, and the mammals. So if your dredging operations somehow impact either one of these, there will be someone later down in the food chain that will be impacted. So it means something if you're shattering out algae, it means something if you're shattering out plants, corals, or anything like that, and it means something if you're covering these things. So that's the biology that we'll come back to when Alessandro will start talking about sensitive receptors. And then there's the anthropogenic part, which has a tendency of being seen a lot. It says beaches, water intakes, water quality, its appearance. What do you see from your window in the morning when you look out? And it's the smell. That is not to be underestimated. It's can be quite political. Once you know all this, then you can go back to saying, what is it actually we want to construct and how are we going to do it? It's a dredging method, of course, location and what time of year do you want to do it. It's smart if you have a problem at the bathing area not to dredge in the summertime, or at least in the time where people are bathing. Just to take one thing, and the dredging method governs how much you spill, the speed and so on. And of course, how much are you intending to dredge? And how fast are you going to do it? And what is actually the composition of the things you're going to dredge? And what properties does it have when it is released? And it also depends a little bit on which types of dredger you're using and what you're doing. But you need to know what you're releasing to the environment. Then, of course, spill amounts and grain size distribution, and when you're going to do it. Once you know these things, you can go on to Alessandra. She will take over here. But once you know these things, you can go on to the sensitive receptors. We'll go over to Alessandra.
So thank you, Klaus. Starting from the flowchart that was already presented, now we can focus on this section that is the blue box inside here. And we can say that at the early phase of the project, a crucial aspect is to identify the sensitive receptors. Through a proper system understanding, identify which are the influencing factors in terms of turbidity-related effects. To identify site-specific and receptor-specific turbidity threshold level, and finally select trigger levels to promptly act in order to protect the sensitive receptors. We propose a four-step process, and we are going now to explain step by step all the elements of this process. So the key words that we are looking at together are sensitive receptors, influencing parameters, threshold values, and trigger levels. This approach should be performed based on local knowledge with available data, local consultants, research institutes, user of the water body in question, and historical information, or collect new data through the implementation of environmental baseline surveys. The first step of this process is the definition of sensitive receptors. Looking at this model, we can find the relationship between a source, in this case the dredging activity, and the receiver, the receptor, that is going to receive changes induced by the dredging activity themselves. And they are going to be they may be impacted or receive at least effects by these works. The receptors may include species, habitats, resources and activities, or items located in the area of influence of the project. Changes induced by dredging can be described first in terms of physical effects on the water column and on the seabed. Any change can be characterized by intensity, duration, and frequency. On the other hand, we have the presence of sensitive receptors, and we have to identify them in the context in which we are having changes induced by the dredging activities, and we want to find the relationship between the physical effects on water column and on the seabed to effect or impact on the environment. Any change could affect the sensitive receptor, inducing effects that are only comparable with the local background, or moderate impacts, or irreversible damage, depending on the receptor and its sensitivity, and obviously depending on the intensity of the dredging work. The potential sensitivity of the receptors to dredging works is determined by a combination of their own characteristics and functionalities, and the characteristics of the natural system in which they are located and where the works will occur. And the sensitive receptors are generally adapted to their local environment, to their local ecosystem that can be very different in terms of offshore environment, coastal water, coastal lagoon, and with their natural variation in terms of season, tide, flood, natural turbidity, etc. The second step of the process is to identify and describe the influencing factors that are these parameters that are able to stress the receptor. And this activity is done in order to plan proper monitoring activity and for sure management measures at the end. Elevated turbidity due to dredging can affect the sensitive receptors, for example, through light reduction, sediment deposition, contaminant or nutrient release, or viral phenomena. So looking at these physical effects, we can summarize them in terms of, in the water column, in terms of increase of suspended sediment concentration and turbidity, reduction of light penetration, variation of organic matter and contaminants. On the other hand, at the seabed, we can talk about deposition, increasing mobility of deposition, oxygen variation, less light penetration to the bottom, variation in terms of organic matter and contaminants. All these aspects should be described not only in terms of intensity, but as I said before, also in terms of duration and frequency of perturbation. On the other hand, there are the receptors of these changes, and a list of receptors potentially sensitive to these changes are presented in the paper. And the factors that may influence them are turbidity and redeposition, making two main groups of possible impacts on receptors. Two main groups of receptor are habitat and species on one side, seabed habitats, benthic communities, coral reef, seagrass, fish. On the other hand, marine uses in terms of basic water quality, aquaculture, recreational areas, navigation, and cultural heritage. These receptors are classified as fixed or mobile, depending on their ability to move away from disturbance. This table should be considered as a guidance tool to be completed and confirmed with the site-specific information gathered during the environmental impact assessment study during the design phase before the beginning of the works. Some sensitive receptors are more vulnerable during critical periods, and this period must be taken into account to identify the optimal period called environmental window, in which dredging can be performed with acceptable impact on biological resources. Making examples, for benthic species, critical or sensitive periods of the life cycle are recruitment, deposition, reproduction. Some mammals are only present seasonally. Seagrasses are most vulnerable to coverage during the growth period. Water quality in bathing areas is most important during the bathing season. Going to the next step, we have to define threshold values at which the sensitive receptors may exhibit increasing effects or impacts. This threshold may be defined in many different ways. They have to be defined starting from information about site-specific environmental parameters, their natural variation, and the tolerance of specific sensitive receptors. When a tolerance threshold value is exceeded, the sensitive receptor is expected to experience a certain amount of stress or disturbance. And the acceptability of such effects must always be evaluated against the characteristics of the system where the dredging is going. Threshold levels are often defined as stress levels for a given receptor, and a scientifically sound approach is the use of species response curves that describe the response of individual species as a function of the intensity and duration of increased stress. So making an example, taking the same amount as a moderate turbidity level, we could have different effects if we are looking at the duration of hours or years. So no effect for a perturbation of hours, and mortality for the same amount during years could be a really different extreme with really different extreme consequences. Going in the other direction, if we fix the duration, low intensity turbidity may have no effect, while peaks of very high turbidity may have serious consequences on the same receptor. So using the species response curve approach that I have already described, and the classification proposed by the Australian Environmental Protection Agency that describe effect and impact in terms of acceptable effect, moderate impact, or high impact, we can arrive to define a series of threshold levels at which the receptor undergoes effects or impacts with increasing severity. The relationship between the physical effects that we described and, on the other hand, the associated environmental effects or impacts on the specific receptors, considering their tolerance levels, can be derived on the basis of site-specific data, literature data, or by expert judgment. For this purpose, site-specific data should be available and or inferred by a direct experience from previous projects or specific tests performed on sensitive receptors. The critical aspect is that these site-specific data are often not available or useful, and it may be necessary to perform a baseline monitoring campaign in order to determine before the execution of works the variation in natural levels of turbidity and reasonable and realistic threshold. This process, with the interpretation of the baseline monitoring dataset, represents a complicated matter. This is a task that requires local insight and specialistic knowledge. The last step of the process is the definition of trigger levels for each receptor. A trigger level is the turbidity level that needs to be respected to ensure that the threshold levels are not reached. It is a specified criterion used for the management of the dredging operation. When a trigger level is exceeded, the need for a management action will be assessed, and if necessary, implemented to prevent undesired or negative impacts. A typical approach is to define three different types of trigger levels. A warning level indicating an increase in turbidity levels, providing time enough to investigate the causes and anticipate or identify possible solutions. The action level indicating that the levels have continued to rise and that mitigation measures need to be taken to prevent the impact level from being reached. An impact level indicating that the increased turbidity levels have the potential to harm the sensitive receptors and that urgent action needs to be taken to reduce them below the impact level or the action level. Trigger levels should be monitored either at the receptor, or a location at which the response of the receptor is known. There are many different ways in which trigger levels and monitoring programs are defined worldwide. The elements to provide a clear definition of limits and the development of a monitoring program that can effectively be implemented are monitoring parameters, intensity and duration, location, frequency, depth, and you may find more details in the paper. A good monitoring strategy should be defined in order to guarantee the environmental protection, still allowing for dredging in a cost-effective way. This activity needs to start from the analysis of the sensitive receptors, and the framework that we propose is built for this purpose. Now I give back the floor to Klaus for more detail on turbidity monitoring.
Great, I'm now unmuted, that's fine. Okay, a few words on the monitoring. I'm getting some annoying things here. Here. My screen is there you go. A few words on turbidity monitoring. It's as Alessandro said, it's important how you define your measurement and where you do it, but it's also important that you understand what you're actually trying to measure and how you do it, which devices you use and what these devices are able to do. Roughly, turbidity measurements can be divided in direct and indirect measurements. Direct measurements are measurements that do not need transfer functions. And what do I mean by transfer functions? I mean that you actually measure what you want to measure without having to do anything else. Typical examples include water samples or light dampening, or scattering of light, that's NTU, FTU, and water samples. Sediment traps is another example of something where you simply measure what's in the trap and then you have it. Indirect measurements are actually the most popular measurements nowadays. It's SSC, or remote sensing, especially SSC, where you actually often measure something else, and then you transfer it through a transfer function to SSC. Also, that means the concentration in milligrams per liter or something else. And this transformation is not quite simple. You can transfer light scattering to SSC. That requires water samples. A lot of water samples you have to cover. In theory, all different combinations of concentration levels or composition of sediment. It turns out that the transfer function is also dependent on the grain size distribution. So if you don't take enough water samples, it will probably not be right. And the other way around, if you want to go from SSC to NTU, that's a little more seldom, but that requires that you measure the light somehow, or the light scattering actually. The point is that all indirect measurements require direct measurements to establish a transfer function, and it has to be local because otherwise you're not covering the right combinations of sediment concentrations and sediment distributions. That is one thing. The other thing is that you have to take enough water samples to be sure that this is right. And to put in a little more joker in it, you cannot be sure that the sediment you're actually dredging has the same composition as the local sediment. So you also have to kind of think of how does this react when you get the grain size compositions you see in the dredged sediment. So there are some things about seeing concentrations given in SSC, especially SSC, where you have to consider how did they get to that, and is this actually a global truth, or is it something that you have to think a little bit about. So when you run into a turbidity level in SSC, when you know this, what I just said, then SSC can actually correspond to a lot of different light conditions, because the grain size distributions can be anything. So if you want, if you take a simple example, I mean, if you have a concentration of 100 milligrams per liter in a liter of water, if you put in a rock of 100 milligrams per liter, then you have a concentration of 100 milligrams per liter, but the rock only dampens the light in the small point where it's lying. But if you throw in 100 milligrams per liter of mud, there will be no light at the bottom of the jar. So when you met with this, think about how is this transfer function established and how general is it? That's one thing. Typical devices for monitoring turbidity is, of course, water samplers. That's very common. Optical backscatter, that's also very common. It has limitations, but it's probably the most used device nowadays. There is the LIST, which is also an optical backscatter, but a lot more refined. Not so used yet, but it's coming. ADCP is coming, that's sound. And of course, you have sediment traps. Each one of these has good things and bad things, and to use which one you want to use depends a little bit on which environment you have, what you want to measure, and how you're going to do it. But think about which pros and cons each device has. There is no such thing as a perfect device. I have seen commercials for some of these devices saying that it does not need calibration. That's simply not true. All these devices need some level of calibration, except for the sediment traps and the water samplers, which are direct measurements. Then you need to choose a strategy which fits both the environment you want to protect and the operation you want to monitor. And why is it important to say that? It is because if you have a moving operation, you need also to have some sort of monitoring strategy that follows the operation. It can either follow the operation or it will have to be sitting at the sensitive receptors in the way Alessandro described. Then be clear on where to measure and what you want to measure. That's about the same. It's not enough to say, okay, I want to measure something loose. You have to say, I want this area to have this level. And we are measuring absolute concentrations, or we are measuring total concentrations or excess concentrations, really, and how you're going to do that. So you have to be very clear on what we're talking about. Are we talking about the background concentrations, or are we talking about the background plus the dredging concentrations, or are we just trying to derive the concentrations that come from the dredging? It's very important to be clear on these things. And then you have to define a sufficient, environmentally speaking, practical and low cost monitoring or cost optimal monitoring strategy, which means that no one has an interest in setting up something that's not possible or something that has excessive costs if it's not necessary. So you have to define something that fits the problem. It's like buying a suit, you want it to fit. And finally, that comes down to, my screen is somehow fitting here. Anyway, that comes down to the final words, which basically are that the turbidity limits should be based on a system of understanding, like we started with. It should be manageable in terms of this should be something that's possible to do and something that you can actually respond to the warnings you get. This could be based on a clear definition on where to measure and what to measure. This also implies that you have to be quite concise on what you mean by spillage and where. It also means that it has to be based on site-specific and based on critical shear stress levels for local sensitive receptors. And when we knew that, that was what we basically started with. Then we have developed this set of steps that we end up with now. And it's basically what we've been going through here. It is to develop a system understanding, to identify receptors sensitive to turbidity, to determine shear stress levels for each one of them, and then choose a measurable stress level, and then determine the trigger levels that need to be respected, and finally determine where the limit applies. That's where to measure, based on the influence areas and sensitive receptors and the dredging plan. At the end of the day, you come up with a sufficient practical and cost-efficient monitoring strategy. That is what we're basically saying, that you cannot just come up and say, okay, in this country we go with 30 milligrams per liter, that's what we go for, because that can mean anything when you're looking at what the transfer functions could be. It should be based on a broader understanding of what you want to do, where you are, and what the background concentrations and the background turbidity is, and which sensitive receptors you have. That is basically the message we're passing here. So that was the message for today. We of course have we're open for questions in a moment. There's a little bit of, I'll do that at the end, but there's a little bit of things that you can look for in CEDA. There's a course that I can't, for sustainable infrastructure, and there is, whoops, and there is a next event, of course. But now I think we're open for questions for the next 10-20 minutes, I think. So if you have any questions, now's the time to put them.
Okay, thank you, Klaus and Alessandra, for presenting the paper to us in this challenging way of a webinar. Thanks for that. So now we can take some questions from the audience. So if you want to ask a question, you can raise your hand. You have a button somewhere in the GoToWebinar tool to raise your hand, and then we can unmute you and you can ask your question to all of us who are attending. So, any questions? Yes, I can see at least one person who raised a hand. So I will unmute you now and let you ask your question. Yes.
Yeah, a short question actually. Can you say something about numbers? What are the turbidity numbers allowed, or what is the danger? What is the yeah, we need to measure, but we need to know what we are measuring.
It's quite unclear. I can't hear half of it.
Mm-hmm.
Frederick, could you hear me, or is it from my side? Can you hear me better now?
Yeah, we hear you clear now, but we only understood half of your question. It was a bit
okay. Let me repeat it shortly.
Yes, please.
Can you say anything about numbers? What type of numbers are dangerous in turbidity and what not?
I think that's Alessandra.
I really can't understand the question. What is dangerous?
The question is whether there is a general number for instance, corals or something else that is dangerous.
I think that the answer is no. It depends on the site, on the project, on the receptor, and also on the status of that receptor. So there is not an absolute number. And this is why we are proposing a method, a framework in which you can understand the system in which you are working with and to define local and reasonable values. You can go with the first try after a short monitoring if you don't have time, but then you can go back when you have verified your measures. So there is not an absolute value, even if you have a number in mind. And my answer is no in absolute sense.
Okay, Thank you for the question and the answer. We will move on to the next question from Mahesh from India. I will unmute you now to allow you to ask your question. Yes. Maybe you have to unmute yourself as well. Oops. No. Okay, this doesn't seem to work, so we will move on to the next question from Peter de Boer. Yes, Peter.
Yes, thank you. Can you hear me, Frederik?
Yes, we hear you.
Yeah,
Please
we
go
hear
ahead.
you nicely.
First of all, thank you, Klaas and Alessandra, for the nice presentations. And I was wondering if it would be an idea to use the method to set criteria for certain areas where a lot of dredging is taking place. How do you think about that idea?
Well, it's within the way of thinking. If the area is not too big and you can, do it once and then have a number of dredging operations in the same area and evaluate under the same criteria, you can do that. That makes sense.
Yeah, because in the Netherlands, we also have to do dredging in a lot of Natura 2000 areas. And there also we need to make ecological work protocol. So I think this is a great method to use to underpin such protocols. Thank you.
Thank you.
Okay, thank you, Peter, for your question and statement on that. We will move on with another question from Susanna Lizondo. Yes, I can hear you now.
Hi, this is Hassan from Arab. Can you hear me?
Yeah, we can hear you.
Oh, well, thank you firstly for the great presentation. Really good, really informative. So my question was, and the methodology you laid out was very clear. So my question is that how much of this methodology do you think should be prescribed by, say, a consenting body or an environment agency, and how much of it should be developed in coordination with the contractor? I mean, is it a process of development post or pre-tender, do you see, or a bit of both?
It's a bit of both, I think.
Yeah.
I think it will always be a collaboration between all the parties in the process. So it comes like Alessandra said, you can do some initial stuff and then you can update it along the way. So it's kind of a process. And as the diagram also, I can't remember which slide, where it's an iterative process. You come with an input and does this work, does this not work, can we accept this, is this not? And it's not like you have a rock hard limit somewhere. You accept something at some level. So it's a process.
Okay, understood. So it sounds like it's a process and it's to be developed throughout. So there are some hard limits that might be set with a consenting body, and then it's up for discussion probably post-tender in order to understand what turbidity levels the receptors can actually take, and in view of the baseline monitoring, and to put together an implementation plan after that works.
I would anticipate something like that, yes.
And so, sorry, just the last question. So in terms of sort of highly sensitive sites, is there a place where sort of example limits of what's measured and the triggers can be found, just on some high profile projects or something like that?
There are a few places where you can find something like that. There is a PIANC paper on corals.
Okay.
You can find some of that, and you can find it in various EIAs around the world. I think you can find some of it in the EIAs for the Fehmarn Belt, for eelgrass and stuff like that.
Great.
But that's site-specific, I would say. But if you have the same species, you can have an idea. Yeah, well, I don't think there is a paper that shows everything. It isn't,
Yeah.
because
Okay.
that's also basically what we're saying, is that it's local.
Yeah,
Got
but
you. Got you.
can I add something? You can have
Yeah.
a good basis on the paper. If you read the paper, you can have a list of papers that could be at least the first reference. Then you can check other
Yes.
programs. Yeah.
Fantastic. Understood. Thank you, guys. That was really good. Thank you.
Thank you.
Okay. Well, we have a few more questions. First, we have a question from Bart de Maarschalk. Yes, you can say a question.
Bart de Maarschalk from Flanders Hydraulic Research. I was wondering if you have any suggestion in the whole process of setting up the trigger values and the measurement campaigns, how to deal with the uncertainties of the measurement itself.
That's a long story. If I had the perfect answer for that, I would get a job anywhere in the world. And now you have to evaluate that from place to place, how big the uncertainty is and what the spreading is of your measurements. And then you have to see what the uncertainty is. I mean, if the most projects don't have a lot of measurements, but some of them do. And if you look at the measurements and see how much they spread, then you have an idea of what the uncertainty is, and then you can kind of incorporate that in what your trigger levels are. To take that into account. That's the only way you probably not the only way, but that's the way I would do it. But I've seen several ways of handling that, and it's from place to place. You look at what it is, and then you develop an approach to handle it.
Okay, we still have another question from Charlotte O'Kelly. Yes, yes, there you are.
Hi, great presentation. I'm contacting you from TechWorks Marine. We're based in Dublin. Great presentation. We're involved on the monitoring side, and I was really happy to see remote sensing in one of your slides and satellite data as a way to measure. And then your next slide said about local validation. So we've been doing quite a lot of work with the European Space Agency, looking at using satellite data validated for turbidity monitoring for dredging applications. And I was wondering, do you have any recommendations with regards to the use of Earth observation as a monitoring protocol?
It's an overview, because it's only the surface you get.
Yeah.
So it can give you an idea of what the concentrations at the surface are, but it cannot stand alone. You have to supplement it with something.
Yes,
but it's really, really good for the spatial distribution.
So we've been linking the two together, but satellite data needs to be validated. And as the previous speaker was talking about uncertainty budgets, the uncertainty budgets of the satellite data also need to be understood for the NTU distribution. So that's why I was wondering if you looked at it or if you had any recommendations.
I haven't personally looked at it in that detail.
Okay. Yeah, great presentation. Thank you.
Yeah.
Thank you.
All right. Then we have a final question from John Ball. Yes, if you unmute yourself, John, then we can hear you.
Okay.
Yes, there you are.
Yeah, thanks for that. Really good. I guess my question is kind of a strategic one. It was mentioned that in some countries they just have a limit which they've chosen over the years at 30 milligrams per litre or something. And I just wondered how the industry is going to try and inform those sorts of regulatory bodies that there's a more scientific approach which could do everyone a good job.
Well, that's what we're trying to help with here, because I also ran into those limits more or less all over the world. And as we stated here, if you come up with, say, 30 milligrams per liter, just to take an example, that can mean everything from no environmental impact to a huge environmental impact. So it doesn't make sense. So what we're doing here is saying, okay, here is the tool that you can use to take up the discussion. Have a look at this. Let's try this approach. It's better, it's cheaper, it's, yeah. More visible, yeah. And that's what we're trying to do. So I'm hoping, or we're hoping that the industry can use this, and also the environmental, that goes both ways, can use this to get a more realistic value, because I mean, and you know, 30 milligrams per liter may be very extensive, and it may be way too low. And if it's very extensive, then it becomes way too expensive to do the operation. If it's way too low, then the environment is going to suffer if you do the operation, and no one will ever know until it's too late. So we're basically saying that if you don't set it right, it's going to cost. Just matter who's going to pay. So it's kind of a tool you can use to take up that discussion.
So your suggestion is to use these papers and outputs as your first educational work for your regulators to try and get them on board.
Yeah, and say, okay, look, read this.
Yeah.
Then let's talk.
But it was written by all the stakeholders, so each of us has to have the framework as the same vocabulary, let's say. So as a regulator, I cannot just say, no, this project is not good, but I have to say, this is what I'm expecting to see in your project. And if you present your project to me, you are not supposed to give me a number, but you are supposed to give me the framework in which you propose this number and why you believe that this number is okay for your place and your project. And then we can argue, discuss, and take a solution. So it's a shared process.
Okay, thank you.
Okay, great. I see there some questions were asked as well on the question tab, but I think they all came up already in the oral questions. Yes. Oh, another one is coming up there. Yeah. I'm just wondering how many questions we can take and how long we can continue after 3. So please give me hints. We will address one more question.
That's okay.
Now. So there's one question for you, Alessandra, about for fish and grass beds. Do you have examples of monitoring regimes from previous projects, like trigger levels and monitoring points? Is there any information available on that?
As I said before, in the paper, there are more details, and there is a bibliography at the end as a starting point in which this information can be found.
Okay, that's fine.
And the table that I presented gives a starting point for different receptors and different influencing factors. Starting from that, you can have the framework, as I said. But in the bibliography, you can find references.
Mm-hmm. Okay, thank you for that. Then we also have one question about more information on the list. Klaus, can you say something on that?
Yeah, www.sequoia.org, I think.
Okay, now you're making some promotion here.
No, it's not. I have no stocks in that, but that's the company who makes it, and they have a very nice homepage where you can read about it.
Okay, that's great.
It's also on Wikipedia and Coastal Wiki, and yeah, and it's nice descriptions in all places, written by Sequoia, of course, but nicely described.
Okay. And then we have a question from Suzanne van Lieshout about an overview of available projects in which turbidity limits have been set or acceptable limits have been set. But I think you mentioned already something about that.
You can find it. Turbidity limits. It's hard to Google. It's hard to find exactly. You have to go into each individual countries on their environmental protection agencies' homepages and find out what they think in that country. There are a few papers around. There is one paper that shows all the turbidity limits in the US, for instance. There is about 60 or 80 turbidity limits in the US. There is, you can find it in the Arab Emirates. They are also they flash it if you want to see it. You can find it in there. You can find it you can find it, but you have to fish it out for each individual country. I haven't seen anybody who written a paper which has everything yet, and it would have to be a dynamic paper because they change every year. So no, there is no place where you can find it for everything. You can find a good one for the US, but for the rest, you have to fish it out at each individual country's environmental protection agencies.
Okay, thank you for that. I think we are done with the questions. So I'd like to thank Klaus and Alessandra for presenting results, but also the whole entire working group who helped you in producing the paper. So thanks a lot for your excellent work on all that. The last thing we want to mention is that there will be a next CEDA webinar on effective contract type selection for dredging works next month on 19 October. So you can also register for that. And finally, we also want to mention that together with IEDC, CEDA has produced a book on dredging for sustainable infrastructure, which you can purchase through the website of CEDA, and that there will be also a course on this same topic on 1 and 2 December in Delft, if I remember well. So you can also find more information on dredging and environment there. So I think we now came to the end of this webinar. I want to thank all you participants and attendees for being here and showing your interest in this topic. And yeah, thank you for that. And I wish you a good day. Thank you.
Thank you.
Thank you.